Hey guys, so I'm just gonna re-record this because honestly, the first part of a recording from Wednesday's meet messed up. So I'm just gonna, just for everyone who wants to watch this video, I'm just gonna re-record this. So in Wednesday's meet, we talked about object-oriented programming in Python before we even got to linked lists and other implementations. This is important because those concepts kind of rely on object-oriented programming. And the first thing you need to know is that object-oriented programming is a programming paradigm that focuses on the idea of objects. So what are objects, you might ask? Objects are extremely just simple. They are basically ideas that are represented in code. For example, let's take the idea of a dog, right? A dog can have multiple species. Like there's multiple species of dogs. There's a German Shepherd, there's a Golden Retriever, there's other types of dogs. There's like many. But in general, they're both dogs. And they both have similar features. They both have 4 feet. They both bark. They both wag their tails, and such as that. There's some sort of repetitive idea or features that they both have that object-oriented programming would allow us to represent those ideas or represent the idea of dogs in its feature in code, so we can use it to create templates to represent multiple breeds. So for example, a dog is a dog, but it also has there's multiple species. Like we can say we can be general and say that a dog, it's a dog, and it has a species name. It has a real name, like the name of the dog, and it also has a color, like dogs might have different colors. So we want to represent this idea based on object-oriented programming, and the way we do this is by using in Python there's syntax to allow Python to become an object-oriented language. And the first thing you want to know is class, and then we type in the idea of what we want to create. Dog, in this case, just know that Python or any other language expects you to make the name of the class, capitalized. It's not very important to know, but it's good programming style to always have. And then you want to know how do you even get a dog? Okay, so once we do this, basically the end result we want to do is I will show it out. The end result we want to have is what we just want to have something like hello is equal to dog, and then the species name, and then the name of the dog, and then its color. And we want to reuse this idea multiple times, like Karl, Arib, and then I'm so sorry for the background noise, by the way, and then Jason. We want to reuse this idea to create multiple instances of the dog class with hello, Karl, and this is a bit bad name, with Amit, Karl, Arib, and Jason all being objects of the dog class. So the way we're going to do this is we are going to have a definition. We're going to create a function that has a built-in, which has the name of init, and this is just a built-in function from Python that tells it to that this is the method we're going to construct an object from the dog class. And we use the first thing you need to know is you need to have the self parameter. So eventually we're going to this is used for adding multiple fields. We call these fields, or we call these features fields, that are properties of this class. So we're gonna have species, so I can spell, and we want to assign its species. And then we have this name too, and I just messed up, and then name. And then finally color So these are the properties we want to have, and the way we're going to have this is by having the self keyword that refers to the object itself. Yeah, that refers to the object itself, and then it allows it to have these, I guess, parameters or fields. And we're going to have the parameter itself, and then we're going to have, like, just call it name. So one of the things I mentioned during the class, or the class itself, is that Python has type hinting, which means that you can tell Python what kind of type you want the parameter to be, and this is done by having like the syntax, name of variable, colon, and then the type. Basically, we can make sure that we can remind ourselves. This is like to self-document the code. So imagine I'm writing like 1,000 lines of code. I can just, in my IDE, press Control K for me, well, Shift K for me, and then it will tell me what the type of the parameter is, so I can make less mistakes going on. And then to print it, we just have to have a toString method in Python. Well, in Python, the toString method you would think of in other languages, like such as Java, is something called __str, and it takes the self keyword, and it will return self.name. We're just gonna return self.name. So here I will finally delete 3 objects, right? And then change there, and then we will have, like, I don't know, a German Shepherd as a species, and you'll have the name Amit, and then we'll have the color white. It doesn't really matter, just here demonstrating. So with this object-oriented programming, we can reuse code. We can reuse code. Here, just give me a second. I'm just typing out these parameter names, and then here we can reuse code to basically just create a lot of instances of the same objects. Now we do print Amit. Here we can see that once we run the code, well, I run the code in a special way, we can see that there's we printed out these, well, the name of the this might not seem useful for small code, but object-oriented programming definitely has its place for just allowing to have more of a concrete structure. So say you have like a large project and you want to you have like this idea that you're like reusing over and over again. This is what object-oriented programming allows you to do. And one of the other things I mentioned during our live stream, our meeting, is that these functions, like, you might be wondering, what is __str or underscore init or underscore name? And these are, so anything something, right, is Python's built-in functions for classes. They are called dunder functions or magic functions, and I misspelled magic. Very cool. And then here, just like an example is, so these are called dunder functions, magic function, and they're just built-in functions for Python that you're kind of expected to know for classes. So if we run this code, right, and then do dr dog, here's some included classes that are, since dog is a class and classes already have built-in functions, dogs will inherit all the classes from the object class. And this just doing dr dog or the name of any class will allow you to have some of the methods it has included. For example, I receive the hash function, which means that this is the function that calculates a hash function. It calculates a hash for your object. This is very cool to know because there's some syntax that you will gather along the way. So, and also another question is, what is if name equals main? So if name equals main, well, so underscore name underscore evaluates when it's, so when the program is running in real life time or on runtime, this will get evaluated to underscore main because we're telling Python to run the main library. This is important, just like its syntax programmers use. I'm so sorry for the background noise. Because sometimes we're importing a lot of libraries and we only want to run like our main program or our main script that has a lot of dependencies. So here I already created during the live stream, I created to show this off, I created just a file called hello.py, and I had included was a function called hello that prints out hello, and when we run this, it will print out underscore main underscore and then hello, because as I said before, underscore name when running the main function or the main file will print out to main. But when we imported, even despite the fact that we have these functions, like that these functions are supposed to print, when we import it and then run our code, nothing's going to get printed out. This is because this code block makes it so that only when it's the main function it will run. So what I mean by this is that if we remove that and then do this, it will print out hello. It will print out hello twice because underscore name underscore will be evaluated hello when running from since we're running from op.py. So just to show off the examples, right? We're gonna run this code twice, and this should both print out main. So now that we import it, this should print out hello, which hello corresponds to the name of the file. So this is just a way to, like, if you ever have test code to test out code that you want to like test, code that you want to test out, but you're also importing it. You just have this to make sure that whatever test cases you're testing out won't mess up the output for your main function. Hope that explains everything. Well, see you later.
Is that a linked list has one thing. It's basically a chain of nodes, which means that we are going to be inserting another class of another data type or another object called classes into this linked list. So I guess a question for you guys is, what kind of parameters or what kind of things do you guys expect in a node? What kind of like fields do you guys expect in a node object? As a reminder, nodes have two things. They have a reference to themselves to the next node, and they also have like a data type, like certain data.
Carlos, are you going to implement a singly linked list or a doubly?
Singly for now. So what do you think we should have in this init function? Oh, uh, so first thing is you should definitely have the data. Um, and for this implementation, we're just gonna have data being int. The way typically linked lists in Python work, if you just implement them like this, is that they're generic, which means that they can take any data type. But for like this explanation or this demonstration, we're just gonna have them be ints because that's the easiest way to do it. And well, they have data, and they also have a reference to themselves, to the next node in the list. Unfortunately, can you guys hear me? Arib?
Yes.
Arib, my computer froze. Just talking about classes in Python. So I'm sorry, I'm back again. This time I hope it doesn't crash. So as I was saying, self data, it just takes the data as a parameter. And a node also takes a node also has a reference to the next node in the list. And that is going to be equal none because right now it doesn't reference anything. We are going to change this in the future, but just for now. And also, here's a good thing to know, but in Python, as I said, there's a bunch of dunder functions or magic functions. And if you're experienced with Java, you should know that there's a built-in toString method. In Python, this is technically called __str. So when you're doing, when you're making classes, I would recommend at least adding this, or at the very least, adding __fpr. These are just classes that allow you print easily. I will just show you what this means.
Carlos, I'm disappointed in you. You didn't private that class.
There is no private.
There is.
There is no.
If you put an underscore before the name of any variable, it becomes private. That includes classes.
Oh, I didn't know that. So I'm sorry. But I could have swear that Python didn't have private fields. So what this is useful for is if you do self.data. So now if we create like a node 1 with just 5 parameter, and then we try print it, Python would automatically call this function, and it's gonna just do us the favor of being printer friendly. So let me see, like, wait, can you guys see my the output, the bottom output? I should have asked it before. Or here, 5. I think that should be a bit better. So yeah, just it automatically calls this str function, and when you're making a instance of this, of the node class. There's also, in Python, there's also things called properties, which are technically functions and technically just fields, but it's a weird mix. So I'm gonna call this value, and it's gonna take self. It's also gonna return the same thing. So the good thing about this is that you can now just do dot value, and it will return the same thing as this. The difference is that this will only be called on when you're trying to print the object, and you can use property whenever you feel like it. So I guess you can do like x dot, I don't know, 10 plus n1, that value, and that will work. And of course, this is an int. Well, So that will work. This is just pretty useful syntax to know. I guess, like I said, this is basically me just introducing you to Python quirks and stuff. And now that's the basic foundation of a node in a linked list. We have just a constructor and a print function. Now, for the linked list itself, what do you guys think the fields are going to be for a linked list? Like, what do you expect in a linked list? So a linked list, to make it clear, it's just a series of nodes with a series of nodes, each pointing to the next node. So I guess what I'm trying to ask is, what parameter do you guys expect in at least every linked node?
Someone said node root, and that is technically correct. That is called the head of the linked list.
All right. So we're gonna do self.head. It's equal to none for now, because it's gonna have definitely a head, but we don't know if anything's inserted in the head so far. So for now, this linked list class will work. Now, if we do s.linked-list, and then you do s.head is equal to node .5, this will work. This is technically and you do like s.head.next .node.6. This is technically a linked list, but it's very redundant for me to keep typing this out. As I said before, like object-oriented programming, one of the benefits that allows you to like reuse code, and we don't really want to and create functions based on objects, and we don't really want to keep rewriting this. This is pretty useless. So what many linked lists have is a function called insert. And insert will take a parameter that matches the node, and we will create we create a new node to be inserted into the linked list. I will do this one first because I will ask you more questions, but basically we're just going to create a new node and the value type data, and we're just going to add it, and we're just going to check if self.head is none. If it is, then head will be equal to new node. Else, we will have to okay, this is the most basic parameter, right? So if the head is empty, we're gonna automatically add a new node to the linked list, which will initialize it. But if it's not empty, then we're expecting that we have to go through the whole linked list and to find the end, and only then can we insert the node, because as we define a linked list, we insert the new node at the end. So the way we do this is we do current is equal to self.head, and then while current, basically this while statement is saying, while current is not null, we are going to do current is equal to current dot next. And this is the typical way of how you would just go through a linked list, traverse through linked list. And once this is done, we can do current.next is equal to new node. And that's basically the insert function.
Does that actually work?
I think so. Should.
If you're doing while current, then you exit the loop whenever current is itself none. Yeah. And none.next doesn't have a value. Yeah, shouldn't current.next be in the while? That is correct. You want to find when current.next is empty and then set that reference equal to the new node.
Yeah, yes, you're right. You're correct. Thank you, Arib, for catching my mistake. So again, we're just gonna copy this line and we're gonna do sinsert. And if this works, correctly, well, yeah, to test this out, we actually have to create a print function, which I totally forgot. So again, we're just gonna use a dunder function str. So we're just gonna be able to just do print s. Okay, this should be current, right?
Yes. But you never set what current is equal to start off with.
Very cool.
And this is one of the reasons why for CP you get algorithms ready on your own in a folder, so you don't have to write them.
It's just a demo, but this should work if I'm not an idiot. And now if we and just do like, yeah, you see, now we successfully added new nodes and printed out. Any questions so far about just anything I've done? Let me pull up the chat because I just realized. Oh my God, I have 12 messages. I'm so sorry. Any questions so far? I really can't see the chat, so if I would appreciate if you guys can like speak out your questions.
What does that dot join result thing do?
Oh, so dot join is, sorry, I'm so used to like my other C languages. So this will basically, so result, we're adding all the values to this result array. So at the end, it's gonna look like something like 7, 5, 7, 10, 9. And we kind of want to print it out pretty, right? So the way I did that was by using that dot join function, which just combines all the elements of this array by a delimiter arrow. So it's just going to print out, well, what you saw here. If you can see it, hopefully you can see it. It's just a really pretty way to like print it out. I just recommend doing it. Just like making output pretty. And this is basically just a very simple linked list. And let me just delete.
Oh, implement inserting at any index, Carlos.
I will. Wait, should. I guess. So another thing people might see useful is that they might like want to see if the if the size of the linked list is empty or not. So one of the things you might see in a linked list is also the self field. and basically we're just going to return another under function. And this is basically going to return of that size. So now when we print out the length of S, and then we increase it in our insert function, not like a crazy person. We should see that, or we have added, we now have a function that adds size. So with this, we can do a lot of things. For example, we can, what if we want to remove a node with certain like a certain position? Or what if we want to get a node at a certain position? So the way you do this is by adding a get. Technically, this will be called get at, but in Python you have another thing called
Carlos, stop using dunder functions. Just go on to removing things normally.
Okay, fine. Doesn't matter.
Carlos, dunder functions are actually absolutely useless in every other language.
Okay,
don't use that.
And this will take position. Just index. So this function is supposed to return the node at the certain at a position. Do you guys know the way you would implement this? There's technically two ways. We have there's two things we have to do. First, we have to check if the index is actually within our size, or if it's within our linked list limit, max size. And we have to get the actual node. So do you guys know how you would implement this? Well, first we have to check if the index exists in our linked list, or it's within our size domain. I feel like I did it wrong right there. Wait, is it plus? I forgot. It should be this. Yeah, actually, here. If self-set size is less than domain, that means that we don't have.
Carlos?
Yeah.
So you want to, if index, actually, just keep going.
Okay. Yeah. So we are not gonna be return anything, because that means that I'm just gonna return none because I'm just used to. But we can't. That means we can't return anything because there is no certain index as a domain. And then we just have to check. So if that isn't the case, if the index exists, for example, if we know that the length of
yes, less than or equal to.
Huh?
Less than or equal to.
Okay, I knew that. If self size is less than or equal to index, then we will return none. No, wait. Should I be? Wait, yeah. Okay, yeah, you're right, guys. Thank you. And now, if it isn't, we can finally just iterate through the array to get the node we want. So if this, okay, I'm gonna use standard functions because I like it. It just makes it easier. So if I implemented everything successfully, we should be able to do like that, and it will print out 10 because that is the, well, since it's a 0 to, we're using 0 based indexes, that's technically going to print out 10. And I was discussing this with Arif earlier, but you know, I guess it's worth to show you. So get item, it just does it so you can like use the array syntax where you would like use get a certain item using, well, the certain element based on the index using the array syntax. That's what get item does. So me and Arif were discussing this, and uh, we thought it would be cool if like to show you guys. Well, I thought it was cool to show you guys. So we're just doing this because sometimes in Python you want to do like -1, and now we just using like that implementation, we can just do like -1, negative indexes. So I just thought it was a cool thing to show. And finally, the last thing I'm going to show you with a linked list is just remove at, basically. And that takes an index. So remove at is basically just, we want to remove a node at a certain index, which means that we want the previous one, the node before the previous node we want to remove, and we want to set its next, set the reference to the previous node to skip the one we want to remove and do that. I don't know if it makes sense, but I promise I will show you what I mean. So using the bad syntax I just created, I will do this, and we're going to get the previous node. So what this does is we are basically skipping over the index we want, and we're skipping over the node we want, and just making sure that references match up. And this is the way that you basically will remove. So a linked list just operates with reference. And so everything like removing, adding just works with references. And we do want to, technically, we would like to return something. So I will create a temp that's equal to previous.next, which is the current, which is actually the node we want to remove. And also I will make sure to decrease the size. And now we can use this function to remove any index you want. So here's the linked list right now. And if we do self.remove at 2, this should remove 10. You can see we removed 10 from the linked list. Any questions? Sorry, I probably didn't explain it clearly. So just any questions? Well, if you do, you can always speak out your questions. And that is basically a simple linked list with removing, inserting. So the next thing I want to like do is work with stacks. So for a lot of data structures, there's a lot of ways you can implement it. You know, a stack, you can actually implement it with an array. And, you know, these are just functions that, this is just like a template I created that will create a stack basically with an array. So with an array, basically using the built-in functions of array, dot append, dot pop. And it's pretty useful to have this in an array, but sometimes you just want to like have a better solution or like a dynamically allocated solution. Python is special because the lists in Python, technically you can always append to them, but in all languages, arrays are limited by the maximum number of elements you allocated at the start. So in a lot of languages, you would probably see something like something like 10 elements, which means that 10 is the maximum number of elements you can have. And after 10, you can't add more elements to the stack.
Jumping onto that train of thought, you'd usually implement a different data structure called a dynamic array in other languages.
So,
but in Python, it's unnecessary and not really possible to do without importing other libraries.
Yeah, so it's pretty useful to have the idea of a stack based on array, but you know, I don't like, sometimes it's just not, you want to have a data structure that you can add to automatically. So this is called stack. Well, we're going to be implementing a stack next. In a stack, it's basically you will add an element to the top, and then you will also remove the top element. So what this means is basically if you have an array of 10, 9, 8, and then you want to append to the array, you will always append after, if you want to append 7 or push 7, the terminology is push. If you want to push 7, you will get the array 10, 9, 8, 7. It will add it to, like, if you think of the array from this being the bottom and 7 being the top, you will add 7 to the top. And if you want to, pop, you will be removing the top element as well. So that means you will be removing 8 in this case. That's basically what a stack is. And I'm going to be lazy and just going to copy my previous implementation of Node. So a stack is actually, I feel it's way easier to implement than a linked list, to be honest, just using nodes. But that's just me. So we're just gonna have another init function. And it's also gonna have just self dot, I guess, what do you want to call this? What is the terminology? Can I just call it bottom? That work? Technically it's not bottom. It's top.
You can just consider it the same as a linked list and just call it head if you want.
Yeah, like just call it head, just to make sure that. So here we will have two functions, push and we also have pop. So a push, it's really simple. Um, Basically, we are gonna be always updating self.head instead of like actually traversing through the whole link list. So do you guys know how to do this? Or does anyone know like the way to implement this? Let's also add self.size. Well, first of all, I need to do this. So push, again, we're just gonna be always updating self.head technically, since how's the way to do it? Since we always have to want to deal with the head or like the top of the stack. So the way to do this is just doing new node. I'm just gonna node is equal to, well, actually we also needed data. And then we're gonna do new node dot next is equal to self.head, and then we're gonna do self.head is equal to new node. This will keep on updating the stack to be on top, and I will also copy my so sorry. I already initialized a stack object, and then I added a for each loop, and we're just pushing I, and we're printing S. So the way a stack works is that we're always going to be updating the head, and so we always want to have like the new object come at the top, like the new node always be at the top. So the way we do this is by doing that, like the new node.next is equal to self.head, which basically makes sure that the new node is always at the top, and that the pointer, the next will be the self.head. So every time you, and then you will update self.head to be point to the new node. So basically, every time you keep on inserting or keep on pushing to the stack, it's just gonna it's gonna just like add it to the top and just gonna reference the head, and you're just gonna keep on adding like that. This is pretty much a terrible explanation, and if you have any questions, please ask right now before I move on to pop. Any questions? Okay. So pop, there's one thing in consideration we have to do with pop, and that is if the stack is empty, we obviously can't do anything to it. Wait, hold up. Stop. Pop will do two things. We will pop the top object of stack, and we will return the pop item. So it's going to return, technically, always going to return int in our stack. And the consideration we have to take is that if the stack is empty, we obviously can't pop. We can't pop to an empty stack. So we're just gonna check this by doing that self.size is equal 0. Usually you will have like an empty function, but I'm just too lazy to write it. Like actually, let's just write it. There's like no harm. Wait, why did I do that? And I keep doing that. And now we will call this empty function. And we're just going to return none because you can't pop anything from an empty list. So what do you guys think we are going to be doing to pop the top item? Do you guys know? All right. So basically, we are gonna make sure that, okay, let me think. So we're gonna be dealing with self.head, and we're basically gonna be able to, we're gonna set self.head to .next, because right now at the stack of the top stack, we just have like the head object at the very top, and it's going to be referencing the bottom object to as its next. So we're just going to set the self.head to be equal to, and I think I made a mistake here because, no wait, no, I didn't make a mistake. So we're going to be referencing, we're going to make this pointer to be equal to self.head. But we also want to return, like make sure that we actually return something. So we are going to be returning self.head. And this should work, I think. Debugging, like implementation live is just kind of hard because sometimes don't know if it will work. But let's see, it's empty. Wait, let's see.
Carl, I was wondering, why did you implement a dot is empty, and why did you implement its dot size?
Dot size?
You know that the stack is empty if the head is none.
Yeah, it's basically because a lot of people like to do like I don't know, print self that is empty. So that's why. Like it's one of the functions I always see. So I was like, whatever. But yeah, like Ariba's right. You can do if self.head is none. Well, you're returning none. And then you're popping this. We're gonna pop 9 since it's the top of the stack. And then if we print s, we should see the effect. Any questions like what I've done so far? Like any questions? Like I will, like me and Arif will be answering any questions you have. Like if you don't understand anything, this is the time right now.
You can also mention if you don't understand everything, then we'll just quickly run through it again.
Yeah.
Can you do that?
Okay.
Okay, so class.node, we have two classes, class.node that just basically take have a pointer, have the value itself. Each node has a value, and they also have a pointer to itself, a pointer to the next node. And then a stack is first, what's the terminology you use to read?
Carlos, just do a high level of it. Okay, so to initialize a stack, you have a head value, that's the top of the stack. You have the push method, which adds something to the top of the stack, and then references the next value of the top node to our original head. You have the pop value, which removes our head and then outputs that and makes our new head the value that's the value underneath the original head. And that's honestly all there is to a stack. And I just realized how badly
Yeah,
phrased everything I
it's
said
hard
was.
to like hard to do this. So I'm just gonna explain it with comments, basically. So when you call this push method, I'm just gonna do self.push, and we want to push 3 to this, I guess, stack. This array will represent a stack. You pretend that 1 is at the bottom, and okay, so you want to view this as basically 90 degrees, like this. Like if the array is like linear that way, you want to view it vertically, and you want to pretend the 1 is actually, you want to pretend 1 is at the at the bottom, and 3, and you want to insert 3 to the right, which is at the top. So basically, array 1, 2, you have 2 elements, 1, 2, and then you want to push 3 to the top. We're going to create a node, a new node, the way we created it last time. And then and every time you have, like, since we're dealing with the head, like a stack just deals with the head, all we're basically going to be manipulating is the head. So you're going to have the new node, basically, this new node. So taking into, you always have to tell yourself that a node has a pointer. Yeah. Okay. Thank you, Ari. So a node has a pointer to the next object. So we are making. Let me see if I can draw as well.
Okay, so.
Okay, this is
One
very
second,
cool.
stay.
This is extremely cool now. Here, Ari, clear that out. Like erase your thing, right?
I honestly don't see the drawings anymore after I placed them.
Okay,
It's bugged
so
for me.
okay, so we have this, and this is a new. This is a new node.
Oh, Carlos, it is not appearing for me at least. Is it appearing for
You
everyone
got
else?
It's not appearing for you.
I don't see it.
Oh,
So
man.
Zoom is bonkers.
Okay, can you see that right now?
No.
Okay, I will screen share my whole screen then. Maybe you can see it now. I cannot do this. And maybe if I do this, and can you guys see my screen now? Like that line I made?
Your screen looks so much better now.
Okay, can you see anything I'm drawing?
Not at all.
Boys, I think it's time for me to hit up Microsoft Paint. Well, I don't have Microsoft Paint on Linux. What am I going to do? Can you see that? Okay. And we already have a stack.
Wait, actually, I don't. Yeah, no. You're drawing.
Sorry, guys. Oh my God. So this is a new node. I'm just going to present it by new and this is a really bad and short stack. Okay, right now we have 1, 2, and this is going to represent 3. Oh my God, that is so bad. 3, okay? And this right now is equal to self dot head. Oh, can you type on this? Yes, you can. We're doing it, boys. Oh my God. Head, okay? This is currently head. Um, and we want to add this new node to the stack. So the way we do this is by setting this. Okay, so you know how each node has a reference to the next node? So basically 2 right now, which is a node, has a reference to 1. So the procedure is that basically this new node that's equal to 3, we want to set its next dot next and we want to set that equal to head. That's the first step, okay? So basically, we will be adding this new node and setting it up equal to head. And once we are done with that, which means that technically this node will be part of this stack now. Once we are done with that, this is referencing next 2 now, and we want to make the new node this new node, and we want to set it up to we want to make this new node equal to head, solve that head. So this process will keep on going each time. Did that make a bit more sense? And then basically we're just going to repeat these same 2 steps for each added node. And it's just basically going to be like, this is going to be the new node, like, this is going to be the new node. That's such a bad thing. So this is going to be the new node. Like, I don't know if you can see my mouse. Hopefully you can see my mouse. Oh my God. This will be the, like the next time you add a node, this will be N4. Yes. Oh, that's so bad. I'm so sorry. I was not prepared to do this, but let's go. You know, you always have to do stuff you don't want to. This node, like say we have a new node 4, we're just going to repeat the process of adding the reference to this node dot next to the solve that head, and then making the new node solve that head itself. So each time the new node will become solve that head, and it will be referencing the old solve that head. Hopefully that made a bit more sense now. If you just ask, please tell us, like, or can you say yes if that made sense? If it doesn't, please, like, we'll try to find something else. Hopefully I spelled that right. Is you okay? Say you have like an array of 1, 2, 3. Again, this is vertical. You have to imagine this is this is vertical. Or actually, you can do it.
It's not vertical.
The Q. How do you in Q? How do you spell NQ and DQ? NQ. Okay, whatever. Okay. There we go. Why did I? So there's 2 things you should know about Q. Is that they have 2 terminologies, and this is equal to push, and this is equal to pop. Okay. And okay, and say that your Q right now is equal to 1, 2, 3. Put the NQ will add an element at the end. So once you do NQ, you will have, and say you want to NQ 1, 2, 3, and 4, like you want to NQ 4, it will be added to the back of the list. And then DQ is different because you're going to be popping or like removing the first element. So that means that the Q right now from this state will be equal to 2, 3. Does that make sense? Like that's the basic terminology of a Q. I hope it makes sense. And now to make this easier, you want to implement a queue with um, a doubly linked list. So hopefully you can see this. I think I got a new method where I can do this. Can you see my screen? Ari,
Yeah.
yes or no? Like what I'm adding right now.
Not at all.
Thank you, Ari. Back to the square pace. Yes. So so a normal singly linked list just has two things, right? It has a reference to the next node, and it has a value. Each one has a value, right? So a doubly linked list also has that, but it also has a reference back to the previous node. This is a very bad thing, but just imagine you have like multiple. So basically, you're going to be ending up like a chain, basically, where each thing has a reference to the next object, but it also has a reference to the previous object. And that is a doubly linked list. And that means we have to have a pointer to the previous. And basically, as I said, we're going to be creating two functions for this queue. We're going to enqueue, and it's going to take self.data, and you're going to create a new node is equal to node.data, and if the self.head is none, we're going to make self.head is equal to, like this is the same procedure as a single list. And now you have to do something special. So last time, or here, let me go back to like where I was going.
Carlos, what are you doing?
Okay, let me show. So you see how insert function, so one of the benefits of basically of a dot previous is that you can add a self dot. I'll add it later, but so with a singly linked list, one of the downsides is that this to transverse or to get to a certain node, you have to go through the whole linked list. This is based linearly on the size of the inputs of the length of the size of the linked list, and this you will have to, like, at the worst case, if you have like 1,000 items, it's going to take like at O of n, which is O,000, and that it's not very beneficial to like time. So one of the benefits to a doubly linked list is that you will also have to create, you can by sacrificing some space, you can have a pointer to self.tail, which means that you can use self.tail. So imagine you have like this, right? This is the head. Okay, this is the head, and this is the tail. By sacrificing some space, instead of like always beginning at the head and having to go through the whole linked list to get to the back of the linked list and inserting new node, we can use the tail as a reference, and now we can automatically just start inserting based on the tail. So what this means is that whenever you create a new linked list, is that you can do self.tail.next is equal to new node. So we will be creating a new node. We will be creating a new node here. Let me just insert it here that has a value, a data, and we're going to be pointing. So this is the tail right now, and we're going to be pointing it to the new node. And then we have to do new node dot previous, because this is how the way doubly linked list works. Dot self dot tail. Then when we're going to be able, we're going to reference it back to itself. And now the last thing we have to do is update the tail to be here. And we do this by doing self.tail is equal to new node. Did that make sense?
Yeah.
Okay. So that is NQ. We're basically adding to the back of the linked list, or this in this case a doubly linked list. And then we have another function called DQ, which removes the first element. So basically we will be removing the head always. This will be returning an int in this case. So as last time, we have to check if self.head is actually has something, because if it doesn't, there's no point to returning anything or doing anything with the operation. We're just going to return none. Else, if we're going to create a self.head. Well, we have to remove self.head, and the way we're going to do this is by moving self.head to the next node. So we're going to do self.head is equal to self.head next. And then since this node right now also has a reference to the previous node, we have to make sure that we get rid of that. And we're going to do self.head previous is equal to none. So right now, we already updated this to here, and we're just trying to get rid of all the references. So basically, we're gonna pretend this doesn't exist, and now the head.
I'm gonna return the head.
Yeah, hold on. No, oh yeah, temp is equal to self.head. And then return temp. We're gonna return temp because the way the DQ works is that you want to return the value just last, I guess, removed. And yeah, this is just the two functions that define a queue. And now if we just do, instead of doing this and then doing NQ and then DQ.
Carlos, DQ, it doesn't have a parameter.
Thank you. You see, here we just added it here, and by using NQ, we're adding it to the back. Wait, let me try to do this here. This is going to be awful, but let's just do it. So we're always adding to the back by using NQ, and by using DQ, we're removing the first element. And this is all constant time. So the benefit of a queue data structure is that all the operations by removing by well, I guess in queuing and dequeuing, all these operations are constant time. So they're going to be really quick, extremely quick. And this is all the downside of having a bit more space for each, like if we're talking about space complexity, we have to have a self.tail for a linked list. And for each node, we're also adding a self.previous. But overall, the benefits, it's speed. But if you're having like a competitive program problem where you are required to add, or you're limited by a certain amount of space, This might not be like you can have other implementations of a queue, not using a doubly linked list. But the benefits is that this is extremely fast. So basically, I think we're done finally because I don't think it really wants me to go over the collections library. So any questions over these 3 data structures?